Let's move on to the major apolipoproteins. The apolipoproteins are amphipathic proteins that bind to lipids to form lipoproteins so that the lipids can be carried through the circulatory and lymphatic systems. Do you remember what amphipathic means? It means that they're both hydrophilic and lipophilic. They swing both ways. Therefore, these apolipoproteins can float in the bloodstream while attracted to both lipids and the bloodstream. So there are going to be 5 major important and majorly tested apolipoproteins. We'll start off with apolipoprotein E. Apolipoprotein E mediates remnant reuptake into the liver. This is going to be found in VLDL, IDL, and chylomicrons, as well as HDL. Now, when these lipoproteins are pooped out and depleted, they can return home by the liver by lipoprotein E. Just remember that ApoE is found in every lipoprotein except for sad little LDL. Apolipoprotein A activates LCAT and is mostly found in HDL. Since our LCAT converts cholesterol to cholesterol esters in HDL molecules, it makes sense that ApoA1 is going to be found in HDL lipoproteins. Apolipoprotein C2 is a cofactor required for lipoprotein lipase, which is used for degrading triglycerides in VLDL and chylomicrons. As we'll see in a minute, chylomicrons and VLDL molecules are loaded with triglycerides, so if they express ApoC here, they can find LDL on the vascular endothelium to unload some of their triglyceride cargo. Apolipoprotein B48 mediates chylomicron secretion, so this is found only in chylomicrons. And then lastly, our major lipoprotein B100 is mostly present in VLDL, LDL, and IDL molecules. It's going to function to bind LDL receptors and allow these lipoproteins to unload their products to cells within the body. LDL molecules are typically known as bad cholesterol molecules. ApoB100 isn't always your best friend. Now, if you want to be 100 someday, age 100, hopefully you don't express a lot of ApoB100 markers on your lipoproteins, because that'll dump off all of your cholesterol to other cells. Let's talk about lipoprotein functions. Now that we've talked about what makes up each lipoprotein, let's figure out what they are and what they do. So how are the lipoproteins classified? The different lipoproteins are named according to their density. From low to high density, we have chylomicrons, meaning they're the low density. Then we have VLDL, IDL, LDL, and then lastly HDL. So we start off with our chylomicrons. These are the least dense, while our HDL is the most dense. In general, higher density implies more cholesterol and proteins, less triglycerides, and a smaller size. Therefore, the chylomicrons and VLDLs will have a lot of triglycerides, but less cholesterol, while our LDL and HDL will have more cholesterol and less triglycerides. Now, this HDL is going to be an exception to the trend because its cholesterol content is only moderately high, and most of its density comes from proteins. Let's talk about the chylomicron. Where do they come from? The dietary lipids and enterocytes enter the endoplasmic reticulum, where they coassemble with a freshly translated large apolipoprotein, such as ApoB48. Now this can become a chylomicron, which contains C2 and E. Apolipoprotein C2 and E. From the intestine, chylomicrons enter the lymphatic system and go through the thoracic duct before reaching the bloodstream. Now, what's the function of a chylomicron? The main role of chylomicrons is to deliver dietary triglycerides to peripheral tissue. It's that simple. They want to transfer dietary triglycerides to peripheral tissues. Now, chylomicrons contain mostly triglycerides and only a small amount of cholesterol. The chylomicrons meet the lipoprotein lipase in the bloodstream, which releases triglycerides. These triglycerides can be fed into muscle tissue or adipocytes. Once they've delivered most of their triglycerides to the tissue, what remains is now called a chylomicron remnant. It makes sense, it's the remnant of a chylomicron. And this is going to be transport cholesterol back to the liver. We just saw how triglycerides travel from the gut to the body. From the gut to the body. So now let's take a look at the liver. VLDL, very low density lipoprotein, is secreted by the liver, and it can drop its contents off to peripheral tissues. How do VLDL and chylomicrons differ? Although VLDL still has more triglycerides than cholesterol, it has a higher cholesterol content than chylomicrons. Another important distinction is that VLDL is going to be produced from the liver, whereas chylomicrons are going to be produced in the enterocyte, in the intestine. However, VLDL and chylomicrons are similar, meaning they deliver triglycerides to peripheral tissues. So similar function, but slight differences between the two. Now, after they've delivered some triglycerides, the VLDL remnants are called intermediate density lipoproteins, IDL molecules. Although IDL can be taken up by the liver, it can get further degraded. It's going to lose its ApoE and become an LDL molecule. So it can become an LDL molecule now. Do you remember what apolipoprotein marker is going to be found on that LDL molecule? Well, the main one is B100, and its function is to transport cholesterol from the liver to peripheral tissues. During the transition from VLDL to IDL, lipoprotein lipase was used to allow triglycerides to be delivered to tissues. Remember, they cleave off those triglycerides. Hepatic lipase plays a similar role, and it's going to degrade some more triglycerides from the intermediate density lipoprotein to make it an LDL, a low density lipoprotein. Therefore, in LDL, pretty much just cholesterol remains. Now, this means that cells need to have LDL receptors in order to get cholesterol from this LDL molecule. We'll talk about that more in a minute when we go through the dyslipidemias. LDL has a vital function in the body because it transports cholesterol from the liver to the rest of the body. However, LDL is sometimes thought of as bad or lousy lipoprotein. In large arteries, LDL can get oxidized and trapped in the vessel intima. Oxidation of LDL causes macrophages to recognize it as a pathogen, so they endocytose or become foam cells, which is going to be the beginning of atherosclerosis. Oh, what a scary word, atherosclerosis. You'll hear more about this atherosclerosis in the cardiovascular section, but just realize that high LDL levels contribute to the formation of atherosclerotic plaques. Our last lipoprotein is going to be the HDL molecule. This is the good cholesterol, so we're happy with high HDL levels. Remember that HDL is high density lipoprotein for healthy lipoprotein. This is because HDL basically has the reverse function of LDL, since it transfers peripheral cholesterol, including that in atherosclerotic plaques, back to the liver. When HDL is created, its core is mostly empty. So notice how we have cholesterol from the body. It's going to be loaded onto an HDL molecule, and it's going to be transported back to the liver. When HDL is created, its core is mostly empty, but its membrane has a lot of proteins, which gives it a higher density. Remember, we covered that. As it travels through the circulation, it's going to pick up cholesterol from that body. So let's run this animation one more time. It's going to load cholesterol from the body, causing it to fill up and expand until it ends its journey at the liver. Once the cholesterol gets dropped off at the liver, it can now be sent to the intestines as bile salts, So here's our bile salts. We're kind of piecing together the picture here. Or this cholesterol can get repackaged into VLDL and sent back out to the body. So it can have a couple different routes. Which apolipoproteins are found on HDL molecules? Well, HDL contains apolipoprotein A, which is needed for LCAT activation, but it also has a repository for apoprotein C and E, which are needed for chylomicron and VLDL metabolism. HDL is produced in both the liver and the intestine. Got a flash quiz. Which organs take up low-density lipoproteins from the circulation? What receptors are used for this? The liver and peripheral tissues both have receptors to uptake LDL from the circulation. So the liver can uptake LDL, but also peripheral tissues can uptake LDL. This receptor is specifically the LDL receptor, which recognizes B100 apolipoprotein on that LDL molecule. So, with regards to the question, which organs take up low-density lipoproteins from the circulation, that's going to be our liver and peripheral tissues. All right, let's talk about the things that can go wrong with lipids and lipoproteins. A standard lipid profile is going to measure your LDL, your HDL levels, your total cholesterol, and also your triglycerides. A dyslipidemia is any significant difference from normal values in a lipid profile. High LDL and low HDL are both well-established risk factors for atherosclerosis and coronary artery disease. Do you remember what was the good cholesterol and which one was the bad cholesterol? Well, hopefully you're remembering that HDL is your protective cholesterol, while a high LDL may lead to atherosclerosis and is therefore your bad cholesterol. Very high LDL levels can also cause cholesterol deposits in the skin or the tendons. And these are called xanthomas. Now, if these occur in the eyelids, as you can see here in this picture, they're called xanthelasma. And if they're in the cornea of the eye, it's called arcus senilis, or corneal arcus. Now, if you see these on boards, or if a question describes a xanthoma, I want you to think high cholesterol here. So they may either show something like this, or describe a waxy plaque that's due to high cholesterol building up on the eyes or the tendons. So you see here different examples, all of which demonstrate high cholesterol levels over a long time. We can now talk about the hyperlipoproteinemias. Type 1 dyslipidemia, also known as hyperchylomicronemia, is defined as an increase in chylomicron levels. This results in elevated levels of triglyceride and cholesterol in the blood, although it mostly affects the triglycerides. Hyperchylomicronemia is caused by an autosomal recessive deficiency in lipoprotein lipase, or a defective ApoC2, which is the cofactor needed for lipoprotein lipase. How can hyperchylomicronemia present clinically? Well, it can result in pancreatitis or hepatosplenomegaly and eruptive or pruritic xanthomas. However, it's important to note that this does not increase the risk of atherosclerosis since there are not high levels of LDL present. Type 2A dyslipidemia is also known as familial hypercholesterolemia, and it's going to be characterized by increased LDL levels. It's caused by an autosomal dominant mutation that results in the absent or deficient LDL receptors, as you can see here. Without these LDL receptors, LDL can't be taken up by tissues, and therefore it accumulates in the bloodstream, eventually becoming deposited in the walls of the vessels. This leads to atherosclerosis and vessel wall injury, such as the one shown here in the picture. Then you also see the xanthomas as well. This can also cause the tendon xanthomas, the corneal arcus, which remember was that pale arc around the cornea. Now, type 4 hyperdyslipidemia, also known as hypertriglyceridemia, is going to be an autosomal dominant mutation. It's characterized by high hepatic production of VLDL. Do you remember what VLDL molecules are primarily made of? Well, they're primarily made of triglycerides. So you'll see the increased triglyceride on lipid profile. This mostly causes pancreatitis. That's really it for the hyperlipoproteinemias. Let's do a flash quiz. 35-year-old woman has an MI. On exam, she has an Achilles xanthoma. What is the defect and blood workings most likely? This woman likely has type 2A familial dyslipidemia, which is also termed hypercholesterolemia. This disease results from absent LDL receptors, so LDL and cholesterol levels are increased in the bloodstream. So increased LDL and cholesterol. Alright, the high LDL leads to an atherosclerotic plaque, which contributes to a heart attack, while the high cholesterol levels can be seen in the Achilles xanthoma. Since the patient had a heart condition and xanthoma, it can be assumed, therefore, that she has high cholesterol levels, which is a trademark of that 2A familial dyslipidemia.